In this section 8-2, we're taking a look at two vector operations. And so two of the basic vector operations are scalar multiplication and vector addition. All right? And so those two processes are kind of described in these paragraphs here. And so really the product of a vector and a scalar is the vector that is the absolute value of k times as long, right? And if k is positive, then k times the vector has the same direction, and if k is negative, then kv has the opposite direction of the original vector. Okay? Let's see. So when you add two vectors together, really what happens is it's the sum of each of the individual component vectors, right? And so kind of like in these figures that we're looking at, like if I have two vectors right here and I wanted to add these two vectors together, then if I take the first vector and I take the second vector and put the initial point of the second vector that I'm adding at the terminal point of the first vector, then from here to here, then the resultant vector, u plus v, would be the vector whose initial point is the initial point of the first vector and whose terminal point is the terminal point of the second vector. All right? So if I take the vectors and put them end to end, then the resultant is from the straight vector from the beginning to the end of the other one. All right? And let's see here. And that's kind of what this paragraph is describing there. Let's see. Resultant, when you add them together, it's called the resultant. And so here's the definitions. So if you have one vector whose component form is u1, comma u2, and then you've got v, v1, v2. These are vectors. Let's say k is the scalar, a real number. Okay, then the sum of u and v is the vector. So again, to get the addition of the two vectors, you would take the u1 plus v1. All right, so the first component of vector u, add it with the first component of vector v, and then that's the component of the resultant. Then u2 plus v2, those two components, and add those together, and that's the component of the resultant vector. So we're just taking each matching corresponding part and combining them, adding them together, and then that would give you the sum. Scalar, okay, if you have a scalar times a vector, right, then it's that scalar times each one of the components. All right, each one of the components is multiplied by that scalar, and then that would give you the component form of the new vector. All right. Let's see. Now, there are some properties of vector addition and scalar multiplication. So we're saying that u, v, and w are vectors, and c and d are scalars. Then the following properties have to be true. All right. So u plus v is equal to v plus u. So vector addition is commutative. It's also associative. If I group the first two vectors together, or the second group of, like in other words, if I have a string of 3 added together, it doesn't matter which 2 I add first. If I add 0 to a vector, you get the same vector. Additive identity, if I subtract the vector from itself, the result is 0. Okay. If I am multiplying here by two scalars, it doesn't matter if I multiply the second scalar times the vector first and then take that resultant and multiply it by the vector, right? Or if I multiply the two scalars together first and then multiply them by the vector, they would be equal. It doesn't matter the order. And likewise, the distributive property works whether it is adding, if I were to add two scalars together, right, then I can add those together and then multiply it by the vector. Or I could take those scalars one at a time and multiply it by the vector individually and then add those together. That would still work. Then your traditional distributive property would work. Multiply it times 1, you get the same thing. Multiply it times 0. Then the magnitude of a vector times scalar c is equal to the absolute value of that scalar times the magnitude of the vector. They're the same. All right, so really all of the normal addition and multiplication properties hold true for vector operations. Okay? What are the types of problems we're going to be doing? There'll be problems like this. We have two vectors defined for us, and so we want to find the following vectors. So 2v. Well, if I wanted to find the vector for 2v, then I could just take that scalar 2, of course, by the definition, and multiply it times the component 2, 5. And so that would be the resultant vector of -4, 10. All right. So there we go. And remember, what the component form shows us is doesn't really give us the position of the vector on the graph. In other words, it doesn't tell us where the location of the initial and the terminal point is. It just gives us the direction and can give us the magnitude. All right. Let's see. Now, what about vector W minus vector V? Well, remember, vector W minus vector V is going to be equal to this component, 3, 4, minus this component, which is -2, 5. All right? And so when I combine those things together, I'm going 3 minus -2, right? Because this almost acts as a scalar times -1, right? You can say plus -1 times all this. And so that's going to be 5 for the first component, and that's going to be -1 for the second component, and then that's the resultant. Okay? And one more type of problem they asked me to do, which is V plus 2W and so that's going to be the component of -2, 5 plus 2 times the component 3, 4. And so for this, that first component will remain the same as I go through and multiply out the next one, which is going to be 6, 8. So now that I've multiplied that scalar, I can go through and add them together. So -2 plus 6, what will that be? That'll be 4. And 5 plus 8, that'll be 13. And hope you can see that. There you go.